Okay, we have two classes left to talk about friction, the last topic, and I think that should be plenty. We've talked about friction in one way already. We talked about if you have a friction contact, you know how to treat that in statics. But we're going to go into a couple of other types of friction that come up. So friction. We're going to do these categories. Square threaded screws, belt friction, and two kinds of bearing friction. The first one is called the journal bearing. You can think of that as like a pin joint, like a standard pin joint. And the second one is called a thrust bearing. Well, you can think of that as the friction that would come up in a pin joint due to the thrust that if a pin joint provides thrust, this is the type of friction that would be applied. Okay, so I'm going to start with square threaded screws. So here is what a square threaded screw is. If you picture a screw or a bolt, where the thread looks like this, where the thread is a constant thickness the whole way around, that's square threaded. And that's different than the standard screw or bolt that looks like this. Let's see. Okay. So when would you choose one of these or the other? Like, I don't know, it depends what I have lying around. There's actually reasons, why one would be useful or the other one would be useful. So let me just write out a little list of the benefits of each of these. A standard thread really has one advantage, but it's an important advantage. It's easy to make, and that makes it cheap to manufacture. And so as long as your application, as long as a standard thread works for your application, this is the one to use. Square threaded, though, has a few advantages that make it really useful for large loads. So first, it's, well, the thread has no, well, let's see, the thread has a constant thickness. No thin, tip or edge to break. If you're applying a constant load over this whole surface of the thread on a standard thread, that tip is going to be susceptible to breaking. And then the second benefit of a square threaded screw is if you think of the forces being applied between, I'm going to describe it as the screw moving in the base. So the screw has a thread, the base has a thread, and the screw moves in the thread of the base. If you think of the normal force applied between the screw and the base, there's no horizontal component to the normal force between the screw and the base. Okay, so question?
Why there's not like because they're attached, but so there's no force acting between them?
Okay, so I'll draw this picture out. So think about the screw. Draw a free body diagram of the square threaded screw. A normal force is perpendicular to this surface. And actually, let me draw this more carefully. This has to be, so the thread would look like this. And if you think about the normal force, this the normal force on this surface is this way, or I guess it depends which surface is pushing. If so, there's a normal force like that, straight vertical. Now think about the square threaded screw. Its surface of contact is like that. And so a normal force there is at an angle.
Oh, man, okay. But if the screw only the thread is attached, unlike on the top, like would it be also attached for for a horizontal component or not really?
Would what?
Would it be also a horizontal component for a normal force or just going?
On the regular thread?
Yeah.
Yeah, right. So this has a horizontal and a vertical component.
Horizontal.
This one just has a vertical
Oh,
component.
okay, this is-
And so that's important because Newton's third law says there's an equal and opposite normal force applied to the base. And so the bigger the force is that you apply to a standard thread, the more that standard thread is applying loads to the base that's trying to explode it apart. Okay, so you can get the base to
So we're
to
using more
break
more force on-
with this outward force. That doesn't happen with a square threaded screw.
Okay. Thank you.
Yep. So this causes an outward force on the base. Okay, so yes,
Understand. So the thread does go around like it would on a normal screw, right?
yes,
Okay.
that's right. But the profile is square like this.
Okay. And you put that in by like pre-drilling a hole and then putting it in, or?
Oh, like for wood. So
Yeah.
they call these screws, but think of it as like bolts. It's between two metal, like car jacks are square threaded screws. Okay, so it's two. Yeah. This doesn't really. You can't cut it can't cut its own way, but you have the threads already built.
Okay.
To solve this, so to do square threaded screw problems, we're going to see that it comes down to, it reduces to these problems that you did in Physics 1 where you have a ramp with some angle and you have an object sliding along the ramp with a force pushing down that I'll call W and a force pushing horizontally that I'll call Q. And so it's a little odd to think of the equivalence between this and two threads in contact. So I'm going to talk about how you can make this reduction. Okay, so this is the base. And then the thread of the screw makes contact with the base like that. Can you picture what I'm drawing there? And this screw rotates, and as it rotates, the thread of the screw, which is in contact with the thread of the base the whole way around, just slides up this path. And if you tracked one material point, it would start out at this point in the base, and then it would be in contact with the thread of the base in the back, and then on the other side, and little by little, it would move up the ramp. And there's sort of a counterintuitive thing about friction. One odd thing about friction is that friction force is equal to the coefficient of friction times the normal force, meaning it has no dependence on the surface area of contact. In all the friction problems that you've ever done, the calculation says that if you have a smooth piece of steel and a smooth piece of wood in contact with a surface area of 1 square centimeter, as long as that normal force is the same, that's going to be the same friction force as, you know, something with a square meter of contact, steel and wood. You know, it's odd, and it's not really true, but to first approximation it is. Mu, yes, right.
Wouldn't that technically always be false? Because couldn't you claim that any normal force, i.e. a point force that you apply to an object, could be represented as a distributive load?
Yes, it is. But I guess that's that's true. And so, yeah, I mean, I think what you're saying is like what seems odd about it. That normal force here is distributed over a 1 centimeter diameter circle. And here it's distributed over a 0.3 meter by 0.3 meter square. And if these are the same material and they're both smooth, and you get the same normal force of contact, even though this is distributed over a tiny little surface and this is distributed over a big one, those friction forces are essentially the same, more or less the same. It's odd, but that's what this equation says. You know, this equation says that's all that matters, and it doesn't ask for the surface area. So, we can redraw the screw in the base like this. Bless you. So here's the base, just like it was before. And here's the screw, just like it was before, on the inside. But now, instead of considering that whole thread of contact, we're going to pretend that the thread of the screw is just made up of one little block. So that one little block appendage coming out of the screw represents the entire thread of the screw.
Where would that block be?
Where?
Yeah, or do you just like assume it?
So this is the entire thread is concentrated into a single block. And the thread in the base is angled. You know, it's following this helical path. So somebody looking at this from the side, let's say someone looking over here. What they see is so now this observer sees a ramp representing the base and a block representing the screw. That's the thread. And that's all there is to it. So now all we need to do is figure out what, to do the math. We need the angle of the incline. We need the magnitude of the downward force W in the picture that I drew earlier, and we need the horizontal force Q. And that's all we need to come up with. And then we're going to treat this problem as if the screw sliding up this ramp is just this block sliding up a ramp.
So this graph is you assume it is arbitrarily, it's not like on the screw, but you assume to do it for calculation.
The block?
Yeah.
Yeah, so what we're doing is, so what's happening when the screw rotates up the base is that a whole bunch of, large surface area of thread on the screw is in contact with a large surface area of thread on the base, and they're sliding against each other.
Oh,
And since that surface area doesn't matter for the friction calculation, we're just going to assume that it's a small amount of surface area, all concentrated in one spot, and then we can think of it the way that we have in the past. Okay, so here's the problem that we have. The weight is whatever this screw, whatever force this screw is being asked to resist. That's W. The couple that's being applied to the screw to make it turn is represented for now as a force Q. And then the angle of incline is an angle theta. And we're going to do the same thing that you did in Physics 1 when you dealt with problems like this. We're going to use a rotated coordinate system with the y-axis pointing out of the surface and the x-axis along the surface. In Physics 1, when you talked about this, I think you probably, just went through the trigonometry of, thought of how much of the weight is in the negative x direction, how much is in the negative y direction. We have an easier way to do it now that we talked about rotation matrices. So let's draw a free body diagram and then represent all those loads in the rotated coordinate system. Okay, so we have a downward force W, a horizontal force Q, a normal force that's perpendicular to the surface. And then I guess it depends which way this is sliding. I think I was saying it was sliding up. So let's say it's moving up the ramp, which means the friction force in this case is down the ramp.
Will weight always be negligible in these problems?
The weight of the screw itself, yes. You know, like I said, these square-threaded screws are only used for when you need to apply big forces, and so the weight of a screw is pretty small.
On just about any force would be negligible compared to how much that's going to hold.
Right, right. And if you're not asking it to hold much, you don't use an expensive screw like this.
Exactly.
So W stands for what is it? It's not the weight, right?
What?
The force.
That's the weight of the thing. That's called W because it's usually the weight of something that's being lifted.
Oh, that's it. Okay.
Okay, so for Newton's second law, the normal force and the friction force, coming up with the components is easy. The normal force is in the positive y direction. The friction force is in the negative x direction in this case. But Q and W we're going to have to fiddle with to come up with components. So the rotation matrix, I've always called the rotation matrix Q. I'll call it R this time. We're going from, so representing Q and W is easy in this coordinate system. And then we want to use that to re-represent it in this coordinate system where this angle is theta. So what's the angle that we need to rotate this coordinate system through? Yeah, it's just positive theta. So the rotation matrix R is cosine theta, sine theta, negative sine theta, cosine theta. And then that W force is cosine theta, sine theta, negative sine theta, cosine theta, times, in the standard coordinate system, this would be 0, negative W. And so when you do this matrix multiplication, you get negative W times sine theta, negative W times cosine theta. If you'd rather do it the way you did it in Physics 1, you can, but this is, now we have this new tool, this rotation matrix, and it's useful in a lot of cases where you've done it using other approaches before. And then the second force is the Q force. So to calculate the components of Q in this rotated coordinate system, so cosine, sine, negative sine, cosine, times. In the non-rotated coordinate system, what are the components of that Q force? Yeah, positive Q, 0. And when you do that multiplication, you get Q cosine theta, negative Q sine theta.
So most likely those equations like Q cosine theta and negative Q sine theta are the fixed equation if we're using it for like problem. We use this equation for
No, you. Yes, actually, now that I think about it, yeah, I'm not planning to give you these equations. So yeah, you're going to have to know how to derive this stuff. Yeah, and you don't have to use the rotation matrices if you don't want, if you'd rather just do the trigonometry, but you do have to know how to set this problem up.
Oh, okay.
Or know how to do it in your calculator.
Right. And so Newton's second law says 0n plus negative mu n 0 plus negative w sine theta, negative w cosine theta, plus q cosine theta, negative q sine theta is equal to zeros. We're assuming that this isn't accelerating. And so now you just, you have two equations. You can solve this system for, what are we solving for? For Q, I guess. So we're going to solve for the Q that's required to maintain a constant angular velocity. Yes? Well, the other two were already rotated. So if we were to use the rotation matrix on this one and this one, we would first have to represent them in this non-rotated coordinate system, which would be unnecessarily hard because we can see already what they're going to be when we rotate the coordinate system. This one's just pointing directly in the same direction as y, and this one's pointing in the negative x direction.
Okay, so it's better to think of it as like the two bottom forces, those are already in the angles that we want?
Right. Those are in the axis directions in our rotated coordinate system. These two are in our axis directions in our non-rotated coordinate system, so it's easy to think of what those would be in a non-rotated coordinate system and then apply the matrix. But like I said, if you like the way that you did this in Physics 1, keep doing that, you know.
If we have two forces on the axis of the coordinate system in either way, why go through the effort of making a rotation matrix? Will there just be more forces involved in future problems, or?
So usually you do it because there's an acceleration that's also parallel to the problems that we're doing here don't have any acceleration. I've never thought about that. I don't know. Try it and see if it's just as easy in the other coordinate system. It might be.
Okay.
But it is true that this is the coordinate system that you use when you do these calculations, ramps on inclines in Physics 1. So it's an approach that's familiar, if nothing else. But yeah, that's a good question. I want to try it in the regular coordinate system. All right, so we're going to solve for this Q. Basically, we're going to figure out how hard it is to, for that certain amount of weight, how hard is it to turn this screw. We have two equations. So the second equation says, if we rearrange it, N is equal to W cosine theta plus Q sine theta. And then plug that into the first equation, and you get negative mu times the quantity W cosine theta plus Q sine theta minus W sine theta plus Q cosine theta is equal to 0. And I'm going to keep all the Q's on the left side, move all the W's to the other side. So we have Q cosine theta minus mu Q sine theta is equal to W sine theta plus W mu cosine theta. And now you can distribute out the Q to get Q times the quantity. Cosine theta minus mu sine theta is equal to, I guess I'll pull the W out too, W times the quantity sine theta plus mu cosine theta. And then divide both sides by the stuff in the parentheses, and you get that Q is equal to W times the quantity sine theta plus mu cosine theta divided by the quantity cosine theta minus mu sine theta. Any questions about that?
Did you have solved it using like matrix, or do you have to solve for the normal?
You probably, yeah, most of your calculators would probably let you solve it with a matrix, yeah. You need one that lets you do symbolic calculations.
Even without symbolic, you could just use the coefficients of Q. As in, if you just put Q on the right side, Q would always be on the right side, so whatever coefficient you get would just be times Q.
Yeah, but we still also have this this theta in here too, and the coefficient too. Okay, so what do you think would happen? What did we just calculate? Did we calculate how hard it was to get the screw to fight against the weight, move, like, to lift the weight higher? Or did we calculate the force required to lower the weight? Yeah, we calculated the force required to lift the weight higher, to fight against the weight. And the way that shows up is in the direction of this friction force. We said that the motion has to be up the ramp, and so this friction force is down the ramp. Okay, this was the force Q required to lift the weight. And that showed up because the friction force was down the ramp. Do you think it would be any different, the force required to lower the weight? Yeah, it is. And you think it would be a bigger force or a smaller force required? Smaller, yeah. And so now I'm going to do this calculation again. So let's calculate the same steps. To find the Q required to lower the weight. So a free body diagram. Most of the stuff is the same. Half the stuff, I guess. We have the weight pushing down. We have the normal force. Now we're moving down the ramp, which means the friction force is up the ramp. And in order to get this moving down the ramp, we need our Q force to go the opposite direction.
So what the difference is it like when you're pulling or pushing through the screw, or
It's, are you screwing the screw tighter or screwing it looser? If you're making the weight rise, or if you're pushing against whatever force is being applied, a bigger force is going to be required to do that. And that first calculation we did was how to do the math. If the weight is actually helping you do your job, like it is in this case, if you're trying to get the screw to slide to lower, you're going to get a smaller force Q required. Okay, so we could go through all the same steps again, but it's going to look similar. So Newton's second law has 0n plus, this time the friction force is in the positive x direction. So mu n 0. The weight force is still exactly the same. Negative W sine, negative W cosine. And the Q force is opposite what it was before. So Q cosine theta, negative Q sine theta. Oh, thank you. I just read them. And that's equal to zeros. And now we just have to simplify those, solve for Q. The normal force is equal to negative W cosine theta plus Q sine theta. Plug that into the first equation. Thank you. Okay, that's the last mistake I'm making this semester. This is minus. Okay, plug it into the first equation. Mu times the quantity W cosine theta it says n minus this plus this is equal to 0, so I moved that over the other side. So mu times the quantity W cosine theta minus Q sine theta minus W sine theta minus q cosine theta is equal to 0. I'll get the q's on the left side. So we have negative mu q sine theta minus q cosine theta is equal to w sine theta minus mu w cosine theta. And so q times the quantity negative mu sine theta. I'm going to pull that negative out, so we'll just call this negative. The quantity then is mu times sine theta plus cosine theta is equal to w times the quantity sine theta minus mu cosine theta. Multiply both sides by the negative 1. You get q times, I'm going to rearrange these, but it's still the same thing, cosine theta plus mu sine theta is equal to w times the quantity mu cosine theta minus sine theta. And then q is equal to w times mu cosine theta minus sine theta divided by the quantity cosine theta plus mu sine theta.
Would Q be negative direction or negative value?
Would what?
Like Q would it be like negative value or is it
Yeah, if you wanted to make it a vector, you'd the way we originally drew it was in the negative, negative horizontal direction, so it's pointing in that direction. Okay, so what we see is, did I put this in a form where you can see it easily? If you compare those two answers, when you're trying to slide up the ramp, you have a plus sine theta in the numerator, meaning, the numerator is bigger when you're trying to move it up the ramp. And in the denominator, you're adding this mu sine theta instead of subtracting it. So the denominator is smaller when you're trying to slide down the ramp. And so sliding down the ramp, if you have a smaller numerator and a bigger denominator, obviously that value has to be smaller. And so this is smaller. Yeah.
It's not completely the opposite, but it's like switched.
Right. You just get, when you're going up the ramp, you get addition in the numerator instead of subtraction. And when you're going down the ramp, you get addition in the denominator instead of subtraction. And they both make the magnitude, trend the same way. All right. There are two things left that we have to do. The first one is that you turn this screw by applying a couple. You don't do it by applying a force Q. So we have to figure out a relationship between the couple applied to the screw and this fictitious force Q. That force Q is fictitious because that's a force we're imagining applying to that block, and that block is part of the thread, right? And so that would be like actually pushing physically on the thread of that screw, which you don't do. Instead you turn the whole screw by applying a couple to, some big lever arm at the bottom of the screw or something.
But with the couple moment, it will prevent it from rotation, right? Like it will make it hard to.
Well, it can, couples, any kind of moment can cause angular acceleration, cause turning, or prevent it. It just depends on what the other loads are that are applied.
Oh, okay.
And the second thing we have to do is find the relationship between the lead of the screw and the angle theta. So first, the relationship between the couple and Q. So if this is the screw, think of a radius as the distance from the outer edge of the thread to the axis of rotation of the screw. That's lowercase r. And so if the load that we're applying to turn this screw is a force Q applied at the thread, then the couple M has to be equal to Q times R. Right. And so in other words, that Q, you could write that as the couple divided by R. And so when you're going through your calculation, you could start out with Q represented this way. And then the second thing we have to do, that was the first, is the relationship between the lead of the screw, which is something you could find on a manufacturing, right. Is it? What's that called, Jay? The thing you, the, when you, in your spec sheet, is that a thing in mechanical?
Oh, yeah, we do specs.
Okay. Yeah, let's call it a spec sheet. Yeah, that sounds good. So, what?
Cut sheets is another term also.
What is?
Cut sheets.
Okay.
specifications.
Okay, great. So you can't find the angle of the screw on the spec sheet, but you can find the lead. So we need a relationship between those. And here's what the lead is. So the second thing we have to find is the relationship between lead and angle. So if your screw is like this, the lead is the change in height for one revolution of the thread. I'll call that lowercase l. You hear the term pitch more often, and pitch and lead mean the same thing as long as, if you imagine like an ant or something walking around this thread, if this ant walking along this thread would end up on the next, would end up directly above itself when it got, once it had gone far enough, then the lead and the pitch are the same thing. But if the ant, some screw threads are designed so the ant would do this, and the next place he would show up over here would be 2 up. It has 2 separate threads that don't cross the same path. Then the lead would be the height change from here to here, but the pitch would still be this. So really what's useful for us is the lead. Okay.
So pitch would be the measurement between each thread.
It would be how much higher the ant is the next time he shows up on the same side of the, yeah.
But the lead is when you go full revolution or?
One full revolution, how much higher you are.
Oh, how much higher?
Yep. The pitch is just what's the height difference between adjacent threads. Okay, so if you imagine taking this thread and straightening it out, you get a triangle that looks like this, where the height change is L, that's the lead. The horizontal distance would be the circumference, 2 pi r. And the angle that we want is this. So theta is equal to the inverse tangent of the quantity L over 2 pi r. Any questions about that? The second type of friction is belt friction. Belt friction is the friction that a cable creates when it's in tension wrapped around a stationary, circular object. So, like, for example, if, Rapunzel. This is Rapunzel. She has really long hair. No, I think that's someone else. Yes, that's someone else. Rapunzel just has super long hair, and like princes try to come visit her, but she's locked in this tower. And so they tell her to throw down her hair, and she's like, I'm not doing that. That's going to hurt like crazy. You're not going to climb up my hair. you know? But there's like a pole out here. And so what she does, because she's an engineering student, is she wraps her hair around multiple times around this pole. Okay? And then the prince, here's the prince. He can climb up the hair now. Yeah, it's Robin Hood. Okay. So the reason that the reason this makes it hurt less is belt friction. The reason wrapping her hair around the pole reduces pain is belt friction. And so if you have, if the pole, you know, the thing the cable's being wrapped around is this, and you have sides of the cable coming off this way and this way, where T2 is the higher tension, on this side T1 is the lower tension. Yes, very good. Her head is T1, the prince is applying T2. These 2 points where the cable leaves the pole create an arc, and you can define that arc with an angle beta. That angle has to be in radians.
Radians, so not degree?
Right.
Oh, okay.
Then T2 over T1 is equal to e to the power of coefficient of friction times beta. And so if you want to, so like Rapunzel is trying to reduce T1 as much as possible, right? T2 is fixed. T2 is just the weight of the prince in that problem. But she's trying to make the ratio of T2 to T1 as big as possible. And the way she wants to do that is wrapping it through as big an angle as possible around the pole, which means many times around, you know, several times 2 pi. Every time around is 2 pi. Right, so it can be 6 pi, 8 pi, 10 pi, you know, keep wrapping it around, and that ratio keeps getting smaller and keeps getting bigger and bigger. The small tension keeps getting smaller and smaller.
So you could set values you want
Right. Yes, exactly. Okay, so here's an example.
So does, in this example, does mu represent like the coefficient of friction?
That's the coefficient of friction between the cable and the round thing, the pole.
So that's where material comes into it?
Yes.
Okay.
Yep. So you'd get different belt friction between like a rope and steel than you would, between a rubber cable, rubber belt and wood or something, because they have different coefficients of friction.
Does it depend how much you tight it, or depend on how much you like?
Mm.
If it's more tight, if you're like climbing a rope, you have to tight it on top, so it's more tight, so it will reduce produce more tension if you're climbing.
No, that should not affect it. What we calculate here is how tightly you have to tie it at the other end if you're climbing, in order to support whatever weight is there. Okay, so here's an example. Let's say we have a pulley, but it's totally rusted, So this is a pulley that's rusted, totally fixed. And you have 100 kilogram mass that you're trying to lift using this pulley. This pulley would work a lot better if it wasn't fixed. And you're trying to figure out what force you have to apply to lift this, given that the coefficient of, let's say in this case that it's static friction, and you're trying to see how hard you have to pull to get it moving, is equal to 0.4. Coefficient of friction is just a number, and it makes sense if you think about that the friction force is equal to this coefficient times the normal force. Normal force has units of newtons, friction force has units of newtons, so that has to be nothing. So what's the force F required to initiate motion? Well, T2 is equal to 100 times 9.81. T1 is the force that we're trying to calculate. And so 981 over T1, or I'll write it as F, is equal to e to the power of 0.4 times, what's the angle, beta? It's just equal to pi, so 0.4 pi. And so F is equal to 981 divided by e to the power of 0.4 pi. And you get a value of 279.2 newtons.
Why would be the angle pi? Like which one should I look for to find the angle? Is it pi? Pi is maybe 180 degrees, right? No, yeah. Pi is 180 degrees. So
Right.
yeah. So is it
180 because this cable leaves over here. This is T2. This one leaves over here. That's T1.
And the angle.
And so the angle that goes from one to the other is pi radians.
Wouldn't your T's be different? 'Cause in order to get the
In order to
rate
get-
to move, wouldn't your F have to be higher?
F would have to. Yeah, it would have to be.
So your T1, T2
Yeah.
is different.
So what would this be? Oh, so what I did was
How much you
how much you would need to. This wouldn't initiate motion. This is how much you would need to keep it at rest. Yes. To maintain equilibrium. Okay, so now let's say that was part A. Say you still don't want to have to apply that much force. So yeah, that changes a little bit of the wording that I was using describing this. So really what's, like I said, okay, this thing's rusted. It would be better for us if it wasn't rusted. In fact, if what we're trying to do is maintain equilibrium, it works out a lot better for us that this pulley can't move. If that pulley could move, that force F would have to be 981. So the fact that that pulley's immobile makes it a lot easier to hold that in place. Okay, so now part B. What if that cable is wrapped 3 times around? Same question. So in this case, there's the pulley. The force of 981 is on this side. The cable goes all the way around once. That's 1 pi. That's 2 pi. Again, 4 pi. Again, 6 pi. And then another 1 pi to come over here. And there's our T1. So this time beta is equal to 7 pi. So 981 divided by T1 is equal to E to the power of 0.4 times 7 pi, or E to the 2.8 pi. And if you solve for T1, you get 0.148 newtons.
So question, why we use radian for this problem? Is it because it won't work if we use degrees?
Yeah, right. The formula, you can think of the formula as just being defined around radians. You could do a conversion and write the formula in degrees, but usually anytime radians appear in a mathematical, anytime an angle appears in a mathematical formula outside of trigonometric functions, you use
So
radians.
there's no like sine or cosine formula.
Yeah, and the problem is that if you ever take derivatives or integrals and you have anything expressed in degrees, things go out of whack because the chain rule doesn't work. So that's why. Any questions about this? Okay, so next time we'll do the 2 types of bearing friction, and then that's it. And then we'll do the end of year party. Everybody bring 1 Valentine for each person. We'll make little decorative bags and stuff for our Valentines.
You're bringing pizza or something?
No, but I'm hoping there'll just be some sitting here when we get in.
Okay.
So if there is any, then we'll eat it together.
If I bring some.
What day is that?
Yeah. If you bring something, well, I'll happily eat it.
What day is it?
That's Thursday. Yeah. But yeah, and we'll just hope for a couple of pizzas. That would be great. Maybe I'll ask our department chair if she'll bring some in.